Hello everyone, welcome to my video. My name is Yumin Zhao, a PhD candidate of SGP. In this video, I will share with you the project monitoring running activities in an outdoor environment with a seismic sensor during COVID-19 pandemic, and these are my co-authors. The ongoing COVID-19 pandemic outbroke last year and spread across the world. Many countries carried out lockdown measures to mitigate the COVID-19 pandemic. The government of Singapore implemented the nationwide partial lockdown, or the so-called circuit breaker measures, on April 7, 2020. The CB period lasted about 2 months. After CB ended, three-phase approach has been adopted to resume activity safely. These three phases are Phase 1, safe reopening, Phase 2, safe transition, and Phase 3, safe nation. During CB, it's mandatory for people who work at non-essential workplace to work from home. We had to have meetings online and take care of kids while working. The pandemic makes people realize how important exercise is to keep us healthy. Working from home saves the commuting time and allows us to have more time to exercise, such as running in the park. To monitor people's running activity during COVID-19 pandemic, we deployed a smart solo in the West Coast Park in Singapore. The smart solo is about 5 meters to the footway in the park and about 7 meters to the harbor drive, where a large volume of motor vehicles enter and leave the 24-hour Pasir Panjang port terminal. As a result, strong noise generated by the motor vehicles were continuously recorded in the data. Besides, frequent sandstorms in Singapore resulted in high-energy spiky signals in the recorded data. And these spiky signals are not acoustic signals, but direct impacts generated by the raindrops when hitting the imposed surface of the seismic sensor. Now let's take a look at the data. First, let's look at the footstep signals generated by runners. We can see the footstep signals are a series of periodic spike signals. Now let's see the traffic noise generated by motor vehicles. We can see the energy of the traffic noise is very strong. Now let's see the raindrop signals generated by thunderstorms. We can see the raindrop signals also contains a series of spiky signals. They can be very easy to be identified as footstep signals. If we put the three different kinds of signals together, we can see different from that of footstep signals and traffic noise. The energy of raindrop signals at higher frequencies does not attenuate much. So if we normalize the spectrum calculated from the three of them, the normalized spectrum of raindrop signals would have the highest energy at higher frequencies. With this difference, we can identify the raindrop signals and avoid counting it as footstep signals. Now let's see how to distinguish footstep signals from the traffic noise and the background noise. We first bandpass filter the data between 40 to 100 Hz, and then calculate the envelope of the filtered data. After that, we can calculate the normalized spectrum of the footstep signals, background noise, and the traffic noise. We can see the normalized spectrum of the footstep signal has very unique characteristics. It contains several harmonics, which cannot be observed from the other two. So based on this, we can distinguish footstep signals from the background noise and the traffic noise. The frequency at which the first harmonic emerges is called primary frequency, which is related to the cadence of the runner. We process 4 months-long seismic data, and this figure shows the average runner numbers in each hour from Monday to Sunday over the weeks during and after SB, respectively. And there were 2 peaks of runner activities, one in the morning from 7 a.m. to 8 a.m., and the other in the evening from 18 p.m. to 19 p.m. Runner activities during and after CB were relatively stable in the morning, whereas runner activities in the evening decreased significantly as soon as CB ended, especially on weekends. We collect the cadence data of the runners, both for the morning runners and the evening runners, and this figure shows the corresponding cadence statistics. We can see the most common cadences are 160 steps per minute and 180 steps per minute. We assume that runner paced at 180 steps per minute and above are fast professional equivalent runners. From these results, we can conclude that people running in the weekday morning on average have a better performance than those running in the evening. We monitor the human running activity change over time during COVID-19 pandemic using footstep signals recorded by a seismic sensor. However, footstep signals can be used for many other applications since they contain rich information such as human flow, occupancy, if there is human intruder, etc. And they can contribute to both urban seismology and earthquake seismology. If you are interested in this project, please check our preprint for more information. Welcome suggestions and questions. Thank you for your time.